It's great to have Mariam Fazal and her team. I'll introduce Mariam and then she'll introduce the team. Here they are part of the Algorithmic Data Science Institute at the University of Washington. Mariam is a professor in the Electrical and Computer Engineering department and has done a lot of work on optimization, so very fundamental work on optimization. And they will talk about optimization models in machine learning, introduction and examples that will include a lot of coding through some of the basic stuff in optimization, sort of the machinery of optimization, how machine learning actually works. Okay, Mariam, take it away.
Hi, thank you, Ariel. Hello, everyone, and welcome to the Optimization Models in Machine Learning tutorial. As Ariel mentioned, I'm Mariam Fazal. I'm a professor in Electrical and Computer Engineering here at the University of Washington. Let me also introduce our graduate student instructors who are going to help teach parts of the tutorial today. They are Kelsey Maass, here. Hello. Kelsey's waving. And Prassana Raut, hey guys, also on the call. They are both graduate students here at UW. If you have any questions throughout, please use the Q&A feature in Zoom to send us your questions. During the tutorial, we'll take a couple of short breaks after each of our notebooks are presented, where we'll try to answer some of your questions. And there'll also be some Q&A time at the end. All right, so let's get started. The goal of this tutorial is to illustrate how we can formulate many machine learning tasks as optimization problems, and how the field of mathematical optimization then helps us understand the properties of the problem and methods to solve such optimization problems. So here's our outline. After a very quick kind of 20,000 feet view of the landscape of optimization models and tools, we're going to focus on a few selected problems that are broadly used in machine learning and often serve as building blocks for more complicated tools. These problems include linear regression and regularization, logistic regression, and outlier removal. For these problems, we'll try to give insights and intuitions behind them rather than detailed proofs. But we also point you to references if you're interested to learn more. You'll also have the opportunity to play with basic models and algorithms using the provided Python notebooks that we will walk you through. All right. So what is mathematical optimization? A mathematical optimization problem has this general form as shown here. Here, X is our decision variable. It's an n-dimensional vector with entries x1 through xn. F0 of X is the objective or cost function. That's something we want to minimize. And if I of X less than or equal to Bi denotes the constraints on the decision variable. These are constraints we have to satisfy. And we can have M of these constraints. Optimization models and algorithms are used in many different fields. In machine learning alone, examples include regression, classification, recommender systems, and many more. But optimization is also critical in many different fields like finance and medicine. Optimization problems belong to different classes. Whether the type of optimization problem has constraints or doesn't have constraints, whether derivatives exist or not, and whether the problems are convex or not. Between these, convex optimization problems form an important class with lots of nice properties. Actually, as Boyd and Vandenberg state in their book called Convex Optimization, with only a bit of exaggeration, we can say if you formulate a practical problem as a convex optimization problem, then you have solved the original problem. So that means being able to express our desired task as a convex problem is going to go a long way. It's extremely helpful. But what's the convex optimization problem? Here's a formal definition. So it means our objective function f0 and the constraints functions fi should all satisfy the following inequality at all points x and y in Rn, so n-dimensional vectors, and for all values of this weight value lambda between 0 and 1. It's actually easier to see what this formal definition means just graphically, looking in terms of the graph of the function. So convexity means a line connecting 2 points on the graph of the function always lies above the graph. Look at the orange line here and the left-hand figure. So in the figure on the left, this holds for all connecting lines. This is one example of a line, but for any pair of points you consider, this is true. And for the function on the right over here, this doesn't hold. For example, this line does not lie above the graph of the function. The most important consequence of convexity is that in a convex problem, there are no local minima, or we can say any local minimum is also global. Of the problems we will discuss in this tutorial, all of them will be convex, except for the last problem on outlier removal. That one is not convex. Okay, how are optimization problems solved? Often there's no closed form solution. Instead, we use iterative methods. In this tutorial, we are not really focusing on algorithms, but we'll mention the workhorse of optimization algorithms and methods, that is gradient descent. Okay, to explain what gradient descent is, let's take the convex case. We have a convex function. Suppose we want to find the minimum of a differentiable convex function f. Suppose we have no constraints. We start from an initial guess x0 and compute the gradient of f at this point. Then we move in the direction of the negative gradient by an amount alpha, which is called the step size, to get to the new point x1, and then we keep iterating, just running through this iteration. Convergence to the optimal solution and the rate of convergence, at least for a convex function f, can be derived by showing how much progress is made in each step, and this depends on the properties of the function. As a simple example, super simple example, here we see a sequence of iterates, x0, x1, x2, and so on, for a one-dimensional quadratic. So for minimizing just fx equals x squared. And on the right, we see it for a two-dimensional quadratic. See the sequence of iterations that minimize the two-dimensional quadratic. So I'm now going to turn it over to Kelsey to walk you through notebook 1 for a quick and intuitive overview of gradient descent. Okay, Kelsey?
Okay, thanks, Mariam. So in our first notebook here, we are going to explore 2 iterative methods for optimization with some examples. In the notebooks, we've added a lot of extra background information for people who want to learn more. But for now, we're just going to do like a really quick overview of what's in the notebook. So as we just saw, optimization problems have this form where you're often trying to minimize an objective function subject to constraints. And very few of these problems have a closed form solution. So oftentimes we solve them using an iterative method. So in this notebook, we're going to look at iterative method for unconstrained problems. So here we just have to worry about minimizing an objective. So we're going to be looking at convex functions, but a lot of the intuition that we get from these exercises are also useful for non-convex problems. So an iterative method generally starts with an initial guess, and then each iteration we generate a new value based on the previous value and then local information, such as the gradient or the Hessian. And then we stop iterating once a stopping condition is satisfied, and this is often specified in terms of the size of the gradient, the difference between successive iterates, or possibly a maximum number of iterations. So gradient descent, the one we're going to start with, it's built upon the fact that the gradient of a function points in the direction of maximum ascent. So if we look at the negative gradient, it points in the direction of maximum descent. So starting with an initial point and taking a step in the direction of the negative gradient, we should be able to arrive at a point that has a lower function value. So here's what our algorithm looks like for an initial guess, step size alpha, and then a small epsilon that we use in our stopping condition. We've provided a lot of information about the initial guess, the step size, and stopping conditions here, but we're going to skip to the first exercise. So here we are minimizing a quadratic, and we're going to look at how the step size affects the solution. So we know our solution here should be at 0, and we can see how the function values and the size of the gradient are changing. So one thing that you don't want to do is choose too small a step size. So in this case, it makes the convergence much slower. And here we actually stop iterating because we reached a maximum number of iterations before we even found the optimal value. On the other hand, you don't want to make the step size too big because then you actually overshoot the optimal point. So here, each iteration, we're actually getting further and further away from our solution. So we want to find the right balance between the two. You could get really unlucky and find a point, a step size where we actually just cycle between points and never converge, but this is really rare in practice. We've included information about setting your step size using what's called the Lipschitz constant of the gradient. So you can read more about that in our notebook. In this case, if you choose that value, you actually converge in one iteration, which is pretty awesome. So the next exercise looks at the effect of your initial guess on your solution. So here, now we're optimizing a 2D quadratic, where here our C variable kind of affects the shape. And depending upon your initial guess, it may affect the number of iteration it takes to converge. So we'll start by looking at this point here. We converge after 43 iterations. But if I choose a different initial point, now it takes much longer, 135 iterations. So what's happening here is we're getting stuck in an area with a really small gradient, so it takes a lot longer to converge. So this is affected by the shape of the ellipsoid that we have here. And we can kind of measure this looking at the condition number of the Hessian. So we can also experiment with these different values. So if I start with C equals 0, now I have a condition number of 1, which is like perfectly conditioned, the best you can get, which means that all of our level sets are circular. So it doesn't really matter where we start iterating. So here it takes 67 iterations, but if I go back to the other point, it also takes 67 iterations. So this isn't considered an easy problem to solve. On the other hand, if I have a higher condition number, now the level sets are kind of skewed, so it's longer in one direction than the other. And now our initial guess really makes a difference. So at this point, we converge after 36 iterations, but if we go back to the other point, it takes 263. So for high dimensional problems, it's harder to visualize what your function space looks like and to choose where a good initial guess might be. But if you can find the condition number of your problem, that can give you some indication of like how hard or easy the problem is to solve. And sometimes using regularization can actually improve the condition number of your problem. Our next algorithm is stochastic gradient descent. And this is a really important algorithm for machine learning problems in particular, because with so much data, it can become really expensive to actually compute the gradient. So instead of computing the full gradient, we just approximate it. So in this case, we're looking at an objective function that's actually the sum of losses for individual observations in the training data. So rather than computing the full gradient, which would be the sum of the gradients of each of these individual terms, we can actually just sample a subset of our training data and then approximate the gradient using that sample. So this is what the algorithm for a stochastic gradient descent looks like, with an initial guess, initial step size, and B. So here B indicates our mini batch size, and this is the number of training examples we sample each iteration. So now, instead of computing the full gradient, we only use B of the terms to approximate the gradient. So one difference here, as opposed to gradient descent, is now our step size is actually changing each iteration. It's getting smaller and smaller. And one reason for this is that because we're approximating the gradient, our approximations can be noisy. So we introduce a lot of variance. So one way of decreasing this variance is to increase the mini batch size. But if it gets too big, you lose the benefits of approximating the gradient in the first place in terms of efficiency. So another thing we can do is slowly decrease the step size or the learning rate using a learning rate schedule. And so what this allows us to do is to take larger steps in the beginning so we can explore more of the function space. And then as we get closer to a good value, we can decrease the step size to kind of converge onto a value. So our first exercise here is we'll explore the effect of the mini batch size on a simple least squares problem. So what we see here is using a batch size of 1, which is considered like true stochastic gradient descent. And we can see with the function values, we have a lot of variance. We're not converging smoothly like we saw before. Here we can see the difference between our iterates, and that's also not really changing smoothly. It's worth noting that in practice, you often don't actually have access to the function value because just like computing the gradient is expensive, also computing the full function value might be expensive. So you might have to approximate it using a subset of your training data, or maybe a holdout set, or you might only compute the full value periodically. But here we're showing it just to illustrate what our points here. So as we increase the batch size, the number of elements we're using to estimate the gradient, we get a much smoother looking curve. We decrease the variance. Now true gradient descent or batch gradient descent would be using the full training set. And here we notice we're taking a lot longer to converge because the gradient's more expensive to compute. But our curve ends up being much smoother. So you guys can experiment with different batch sizes, different max iterations to kind of see the effect of the batch size on not only the time it takes to iterate, but also the minimum function value that you end up reaching. So the final exercise in this notebook explores the learning rate schedule. So in this case, we're using a learning rate that's influenced by this decay parameter. So this influences how quickly our learning rate or our step size decreases. So this is our same example as above, using a mini batch size of 1. And here we have no decay parameter. So we have a lot of variance in our function values as we iterate. But you can play around with changing this value, this decay parameter. And what this does is we have a larger step size in the beginning, and then eventually it gets much smaller. And then you can play with how that affects your convergence, how long it takes to iterate, and then also the function value. Yeah, so that's all the content in this notebook. And now we'll see if we have any questions before we go back to Mariam.
Yeah, so there is one question actually in Q&A. It's about different starting guesses and asking if different starting guesses can ever cause optimization to fail to converge. So I assume that is about a convex, smooth, unconstrained optimization problem as we were discussing in notebook 1. Yeah, so as we just saw in notebook 1, the step size will play a big role, and you can create situations with the wrong choice of step size that you don't converge. But if your step size is chosen correctly for convex and smooth, nice problems, then asymptotically convergence to optimum does happen independent of choice of initial point. So from any initial point, you asymptotically converge. But it, of course, can take different lengths of time. I don't know if Kelsey would like to add anything.
Yeah, I think that's that makes sense. The real issue is when you have a non-convex problem, because then you might end up still possibly converging, but to maybe a less optimal point. That's why we like convex functions. That's
right. Okay, so I'm sharing the screen again, and we are going to continue. Thanks a lot, Kelsey, for going over notebook 1. We'll now see how some key machine learning problems can be viewed as solving optimization problems. Many tasks, at least in supervised machine learning, involve fitting a model to a given data and then using this model to make predictions like class labels for new data. For example, imagine building a spam filter for email given a set of non-spam and non-spam emails, and then using this filter to decide whether a new incoming email is spam. Fitting a model to data is also called training a model. Let's look at the components of such a problem. First, the data. So each pair, AI, yi, shown here, is a data point. It consists of an n-dimensional feature vector, that's AI. So AI1 to AIN are the list of features for the ith data point. And a value yi, which can be a real number, or it can be a discrete class label, for example, 0, 1 for binary classification. What we call the model is the mapping from Rn to R that takes features as input and gives a label or outcome as output. To train a model G, we need to find the model parameters, which here we denote by X. These parameters should fit the existing data well, and then we hope they let us generalize to new data points. We'll see more about that shortly. So how do we fit a model? First, we need to measure how well the model fits the data for a given set of parameters. So that means we have to pick a loss function. For example, the square loss is very common. It's the sum of the squares of output errors. It makes sense to seek parameters that minimize the sum of losses incurred for each data point. Here, the added term R of X is called the regularization function, which we will discuss later. Okay, so that's the basic setup for training problems. We now look at two common problems, linear regression and logistic regression. So suppose feature vector A is just one dimensional. So it's just a scalar shown here on the horizontal axis. Given data points, we want to find a line that fits them well. So this is linear regression. Here, G, our model, is the orange line. It's just a line. And the parameters are the slope of this line and the offset or the intercept. So slope is x1, intercept is x0. So next we should decide how to measure the quality of the fit or what loss function to use. One approach is to assume a statistical model for the errors and look for parameters x0 and x1 that maximize the likelihood of observing yi. And later we'll come back and talk about logistic regression. Next slide is going to be about linear regression. So let's look at a simple case of linear regression, assuming the errors that occur at each data point, that is the epsilon I, are independent and come from a normal distribution. We can write each of these epsilon I errors as yi minus x0 minus x1 ai. So then, because we assume these epsilon I are normal, distributed according to normal distribution and independent, we can just plug in the equation for normal density, that is our familiar bell curve, to get the probability for the ith data point. So that would look like this. And now we can fit our model by finding the parameters that maximize the total likelihood, which is the product of the probabilities for each data point. And this is equivalent to minimizing the negative of the logarithm of this function, which makes the form of the objective simpler. So that's what we're going to do. This gives us nothing but the familiar square loss. The negative of the log of the distribution we worked out is going to be nothing but the sum of the squares of the errors. So the intuition is finding a line that has the smallest sum of distances to all the points. This is the well-known least squares problem. It is convex, smooth, and actually has a closed form solution. Although finding its solution by iterative methods is often more efficient. Now let's turn to a technique called regularization. Regularization plays many different roles. It can help incorporate prior information about the structure of parameters X that we are trying to estimate. For example, we may know that there are only a few active parameters. That means that the vector X will be sparse or has a lot of zeros in it. Or we may know the entries of X vary smoothly across its indices. So for example, if X represents a time series or a signal that's changing slowly. Or we may want the parameter values to be clustered. This is actually useful for feature aggregation. So these are some examples of the type of structures we may want in our coefficient vector X. Two popular examples of regularized regression are lasso regression with an L1 regularization term where L1 norm is nothing but the sum of the absolute values of entries, and ridge regression with an L2 norm regularizer, you often L2 norm squared regularizer, which is the sum of the squares of the entries. You'll experiment with properties of these regularizers in notebook 2. But before that, let me try and give some geometric intuition about regularized regression. For geometric intuition, let's consider the constrained version of the problem. So instead of trying to minimize R of X or put R of X as part of the objective, we keep it small by bounding it with some fixed value T. So that gives us this problem. P can be 1 or 2, for example. We can visualize this optimization problem by thinking of how much we can shrink the blue ellipsoid that represents the objective value while it still intersects the constraint set, which here is shown in red. We see that the choice of norm can influence the properties of the solution. With one norm, the solution tends to occur on a vertex, like this green point here, where many of the entries of X are 0. In this case, one of the two components of X are 0. And with two norm, however, the same thing will result in this green point, and the solution typically doesn't land on a vertex and does not yield a sparse solution. So L1 norm is typically used to encourage sparsity in the vector X. We can move the norm from a constraint into the objective function to get this following problem, which now has a regularization parameter, lambda. Lambda is a regularization parameter that balances model error with how much we regularize, the amount of regularization. Regularization can promote other structures too. An interesting example is in problems called matrix recovery or matrix completion problems that arise in many problems, including recommender systems. The parameters form a matrix X that's often desired to be low rank, to have a small rank. And the regularization for this is known as matrix nuclear norm. We won't have time to go into this, but this is an example of another type of regularization, which is common in machine learning. Let me now turn it over to Kelsey to walk you through notebook 2 on regression and regularization.
Thanks,
Kelsey.
Okay, so now we're into notebook 2. And here we're going to be looking at some regularization, specifically the lasso problem. So problems where we want to have a sparse solution. Unfortunately, the L1 norm with the absolute value isn't differentiable everywhere. So we actually use a variation of gradient descent called proximal gradient descent, which we provided some information here if you're interested. So our first example is a basic least squares problem with one norm regularization where we suspect that our solution vector X is sparse. So it has few non-zero values. We are going to experiment with the value of lambda, the regularization parameter, to see how it affects our solution. So here we see the solution with no regularization at all, just the ordinary least squares problem. In blue, we see the true coefficient values of X, where only about 14 of them are non-zero. But then in orange, we see our solution. So we do a very good job at matching our true output with our predictions, but our solution isn't sparse. So we'll change the lambda parameter to get a sparser solution. So here we do a much better job of identifying a few non-zero coefficients in X while still being able to fit the data pretty well. Now we have to balance this because we don't want to get too much regularization because now we over-regularize. We get almost completely zero solution vector and then our predictions suffer. So it's always a balance. Here we plot the function value, the last value that we're trying to minimize, with the number of non-zeros in the solution. And this enables us to pick a value that does pretty well. So in this case, about lambda equal 1 seems to do well. And here we're plotting the path of these coefficient values in X. When we use really small regularization, we get a lot of non-zero values that are small. And then as we increase, we end up to this sweet spot where we do a pretty good job at estimating the true values. But then if we over-regularize, everything just collapses down to 0. Our second example is a fun one where we're actually estimating a nonlinear model using linear least squares. So in this setting, we have a function that we want to fit, and we know that the form of it should be a sum of cosines, but we don't know the coefficients, we don't know the frequencies, and most importantly, we don't know how many terms we have. But since we believe there should only be a few terms, it's a good candidate for using the lasso regression. So here's a plot of our true function that we're trying to estimate, and then some samples that we take that will split into a training set and a testing set. To set up this problem, we first create a dictionary matrix that contains our training points evaluated at a bunch of candidate terms where we have a bunch of frequencies that we are think might be good values. And then our goal is to solve for the coefficients. So we will set up this lasso problem where we have our dictionary matrix, our coefficient vector that we want to estimate, and then we will use the L1 norm for regularization so that we promote sparsity in the A vector. So here's a solution where we don't use any regularization at all. Our true solution really only had 5 non-zero A values, so 5 terms. But without regularization, we estimate pretty much all of our terms have non-zero coefficients. And then if we look at how we do on our training set versus our test set, we see that we really do a terrible job at estimating future values because we didn't really zero in on the true form of the function. Now, as we add regularization, our coefficient vector A becomes much more sparse, and we do a much better job at estimating the values in the test set. And of course, we don't want to add too much regularization because now we just estimate everything as 0 and we don't do well at all. So once again, we plot our function value with the number of non-zeros. This time we plot it for not only our training set, but also our test set. And this is one way of trying to tune your hyperparameters. So lambda is considered a hyperparameter because it's really more related to the optimization than to our model itself. And one way to choose a good one is to use like a holdout set. And so this plot here indicates that the best value of lambda that we tried was really the one that gave us the best error on the test set. So now we will see if there's any more questions before we move on to the next set of slides.
So no questions yet. Maybe we'll pause. Oh, okay, one question just came in. How do you recommend we set that value of regularization parameter lambda without knowing true coefficients, looking at the optima of the beta coefficients or cross-validation? I think you may have just answered it, but. Oh, actually, yeah. The person who's asking the question also says, I think you maybe just answered it though. Yeah, so the most typical way to do this is through cross-validation, as Kelsey just illustrated on a tiny example in the notebook. But this is interesting and it's a wide topic by itself. What are good techniques of doing cross-validation? Yeah, we have references that include more if you'd like to learn more on the topic. So I think next is Prassana.
Okay. Um, okay, we now turn our attention to logistic regression, which is a framework for doing binary classification. As is usually the case, we might have multiple features or explanatory variables which explain the absence or presence of some phenomena. In that case, like AI would be a vector or otherwise a scalar. For example, if we have some data about the average number of hours students have studied each week and whether each of the students has passed or failed, then the number of hours are the explanatory variables and pass or fail is the outcome. We can also have other explanatory variables such as the number of hours worked by the student on his or her campus jobs. In another example, we can have blood pressure measurement data from patients in an hospital and whether they have any heart-related disease. To understand how logistic regression works, we consider the simple case of one explanatory variable. The goal is to find a linear predictor where x0 and x1 are called the coefficients of the regression model and find coefficients such that when the sum is positive, the outcome is 1, and if the sum is negative, the outcome is 0. If we had only one training data point, this job of finding coefficients would have been trivial. But when we have more than one point, we need to introduce the Bernoulli model, which helps us make correct predictions in a systematic manner. So Bernoulli model has one parameter P, which gives us the probability that an event occurs, and hence 1 minus P is the probability that it doesn't occur. Note that this parameter will vary with the data points as different values of features will give different probabilities. Thus, we can write the probability of the outcome in a clever way. P of yi given pi is pi raised to yi times 1 minus p raised to 1 minus yi. We manipulate this expression to bring it in a form where the log odds terms becomes visible. The ratio of p over 1 minus p is called the odds of the event. If p is 1, then the odds are infinite, and if p was 0, the odds are 0. We model this log odds term using the linear predictor. Putting everything together and multiplying the probabilities of all data points, we obtain the likelihood term. So now we have an optimization problem where we are maximizing the likelihood of the observed data under our model. Alternatively, we can take the negative logarithm and convert it into a minimization problem. Now let's look at one of the terms in this big summation. Call this x0 plus x1a term as z. When the label of that data point is 0, we would want z to be very much negative to get the minimum, whereas if the label was 1, we would want it to be very much positive. The optimal coefficients will be such that they will make the overall summation as small as possible. So in the final logistic curve that we obtain, the center is where the probability is exactly half, and here the feature value is minus x0 over x1. We see that the slope of the curve here is proportional to x1, and thus by increasing x1, we get sharper rising curves, and decreasing it will give us flatter curves. So this optimization problem is convex and smooth, and hence can be solved efficiently, giving us the minima. After we have our optimal coefficients and a new data point is presented to us, we can say that the outcome will be 1 with the probability given by this expression. So there are other methods as well, such as support vector machines, which use optimization to solve the classification problems. Now, let us look at some concrete examples and work them out in Python. So this is notebook 3, and here are some of the derivations and explanations from the slides for logistic regression. So let me begin by explaining the conversion of maximization problems to minimization problems, which we have been doing throughout this lecture. It is not hard to prove that when we compose the objective with a monotonically increasing function, then the optimum point remains the same. And if we negate the function, the minimum becomes the maximum and vice versa. You can see this with an example where if you want to minimize 1 plus 50x squared, and then we convert it into a maximization problem where we are maximizing minus log of 1 plus 50x squared, then the optimal point 0 remains the same. Such transformation might have some benefits in terms of numerical accuracy or some ease of interpretations. Now let's let's look at a toy example. Given here. So, like we have been given some data where like these values, something like the outcome is 0, and for these, the outcome is 1. And like this is the optimal logistic curve that we get using optimization. And we can see the effect of x0 and x1 by changing them over here. So if I keep x1 constant and change x0, we can see that like the center of the curve changes. So that is one effect. And the other one is like if we change x1, so you can see like the center moves as well as like the curve becomes flatter or more sharper as we make it bigger, and decreasing it would make it flatter. So yeah, this is the effect of x0 and x1 on the logistic curve. So now let us look at a real world data set from a study which looks at the distribution of an endangered burrowing spider along the coast of Japan. Here the authors wanted to explore what features were most significant in the prediction of the presence of spiders, and found that the grain size was one of the most important ones. So this is how the plot looks like. For these grain sizes, the spider was absent, and whereas for these grain sizes, the spider was present. Like Kelsey had mentioned in notebook 1, we use gradient descent to solve the optimization problem and obtain the logistic curve. So like we use these values for the hyperparameters, the initial guess, the step size, and the tolerance. And this is what the final plot looks like. Now we can say that if the grain size at a beach is 0.7 mm, then we will find spiders there with probability 0.85. So here are some other experiments which are similar in flavor to those in notebook 1, which you can look at later. Finally, we have regularized logistic regression with L2 regularization, which helps reduce the values of the coefficients of features which don't contribute much to the prediction. We see this as we increase. So this is initially the curve that we have, and as we like keep increasing the lambda value, so the curve keeps becoming flatter, and if we increase it a lot, it will just become a flat curve with outcome 0.5. So now we can stop for some questions, and in the next part, Kelsey will look at outlier removal.
Okay, thank you, Prassana. We have one question that just came in that is asking about packages that implement gradient descent. And the question is, SKE, learn classes, SGD classifier versus logistic regression. Can you talk about differences between those and other approaches? I guess they are asking about difference of gradient descent and stochastic gradient descent. Yeah, they're asking about that. So that was one of the topics in notebook 1. And Kelsey showed that when you do have access to the full gradient for your problem, that's called the standard gradient descent. When your access is each data point at a time, it's equivalent to saying you have access to only part of the gradient evaluated for that data point at every step, then the algorithm is stochastic gradient descent. And new considerations like batch size come in, and more of that is explored in notebook 1. Let's see, any other questions? No, we don't have any other, but let's pause a little bit further. If you still have questions, please feel free to type them in Q&A. And even if you don't get to them in the short breaks, we will come back to them at the end of the tutorial.
Are we ready for the final?
Yeah, let's continue. So Kelsey will do the final part.
Okay, so our last topic is about outlier detection and removal. And for this talk, we're just talking about outliers in a general sense of data that might affect your solution or might not really fit with your model, which could be anomalies in the data, like observations generated from broken sensors, or maybe fraudulent activity, or different types of noise. So there are many different ways to identify and remove outliers. One of them is to iteratively fit your model. So each iteration, you fit your model, remove points that have the highest error, and then resolve. Of course, one problem is that your outliers might affect your initial fit, so it might skew your results, and it's also not really clear when you stop iterating. Another method is to use a robust penalty function. So one example is, instead of using the least squares term, you could use something such as the Huber function, which it's linear for higher values, and then it's quadratic for lower values. And what this does is it doesn't penalize as harshly for points that have a large error. So that means that outliers don't have as much influence on the solution. This works really well for regression settings, but isn't as easy to incorporate into more general models. Our focus will be on trimming, and this is really easy to incorporate for lots of different model types. It has really interpretable results and assumptions. The only downside is it's non-convex. Fortunately, this doesn't really seem to affect things in practice. It generally works pretty well. So this is the formulation for trimming, which all we've really done is we've added this new weight term for each observation, and we're going to optimize these weights at the same time as optimizing our model parameters. The weights will be between 0 and 1, and then we constrain them to sum up to h, where h represents the amount of inliers we expect to be in the data. So if we think 90% of our data is good, we can set h to be 90% of the size of the training set. And as you're training, you will end up fitting the values with really high errors with W's close to 0. So this means that these FI loss values don't have a chance to influence your final fit. And then inliers will end up with higher values of W closer to 1. So now you kind of classify, in a sense, your training data as inliers and outliers while you're solving your model. And then because you've identified outliers, you can also go back and observe what they look like, see why they might be outliers, why they don't fit your model, and give you additional information about what your model is actually doing. It's like we said before, it's easy to incorporate to lots of different types of models just by changing the loss terms. So we could use least squares, logistic. We can even incorporate it into a neural network. So here we have a toy example for least squares, where all of our data here are blue for our inliers, and then we have some outliers here, maybe from like a broken sensor. When we use ordinary least squares, we end up fitting this orange line that's really influenced by these outliers. But now when we add trimming, we end up with this green line, this solution that's really close to the model that actually generated the data. An example with a neural network, here we used a convolutional neural network to train a classifier that identifies either cats or birds in an image. The top row here contains inliers. So these are training examples that were correctly classified, and they had a weight close to 1. So here we see cats that were classified as cats and birds that were classified as birds. But on the bottom row, we take a look at the values that were classified as outliers. So the weights were close to 0. And one thing that's interesting here is we can actually kind of make sense of why this owl was classified as an outlier, because it's a bird that looks like a cat. So it's kind of a funny example. So now we'll look at our final notebook. So here we're going to use trimming to look at outliers for some examples with logistic regression. So our first example, we're just going to fit a really simple logistic curve. The first plot is looking at our linear classifier. So when the inner product between the classifier and the data is negative, we classify it as a 0. And then when it's positive, we classify it as a 1. And then here we plot the probability of our training example being classified as a 1. So we have two parameters that we can play with here, the noise level and the percent that we expect to be inliers. So this corresponds to the value H. So we'll just look at one noise value, but you can go back and play with it later. So we added some noise, so now we have some examples that could be considered outliers. Without using trimming, we do a pretty good job at classifying our data, but we don't do a very good job at really getting close to the true parameters of the model. But now we'll go ahead and add some trimming and see if we can identify these weird points. So I'll say about 92% of my data I expect to be inliers. And now we can see the values that are identified as outliers through the weights are circled in green. And we do a pretty good job of figuring out the points that we want to throw out. And our classification error is even better than before. And we do a better job at estimating the true parameters of the model. Of course, like any problem, there's some sort of trade-off between what values you use. And if you add too much trimming, you'll start to identify inliers as outliers. So let's add a higher level of trimming. So now we start throwing out points that actually were good. So it's always a balance between these sort of regularizers or hyperparameters, different trade-offs that you might find. So our final example is looking at the MNIST data set, which you may have seen before. So it's a set of images that have handwritten digits, and then their labels are the digits contained. We're looking at a subset that just contains zeros and ones, and our task will be to identify if it's a 0 or 1. So here the images are 28 by 28. So our number of model parameters is 784. And we're going to use logistic regression with ridge regularization to solve this. So here we solve it just with standard gradient descent. This is what our classifier looks like, reshaped as an image. And we can see our convergence here. So our classifier is interpretable in this case because we can see that it ends up being negative in regions where the zeros are positive, so that the inner product between the two is negative. And then it's positive in regions where the 1 is positive, so their inner product is positive. So that's pretty cool. Now, we did a great job at classifying the images in the training set and the testing set. There's only one image we misclassified. So let's take a look at that and see if it makes sense. So here's our misclassified image. And it kind of makes sense why it was misclassified looking back at the our solution, because this is maybe a bit more narrow than the other zeros in the training set. But now we're going to go ahead and use trimming as a way to identify other images in the data set that might also be weird in a sense. They don't necessarily fit well with the model that we've trained. So here you can play around with the inlier percent variable. K here influences how many values we're actually plotting. So this is what happens when we use trimming. Our classifier looks pretty similar to the other one. And here we see some of our misclassified, or not misclassified, our outliers. So the images that ended up with a weight close to 0. And an interesting thing to notice here is with the ones, we've identified a lot of images that have these serifs. So it doesn't quite fit with our classifier's assumption that the ones are pretty much just a line. And in this one, it's an outlier because it's oriented differently. So trimming is a nice tool to use, not only to remove outliers from the fitting process so that your solution doesn't get skewed by bad data, but it also allows you to identify observations in your data that maybe don't make sense to what your model has learned. So you can also gain some insight into what your model is actually doing behind the scenes, how it's classifying things or how it's fitting things. Yeah, so that's it. So we'll see if we have any other questions.
Thank you, Kelsey. Let's see which. There is one question. I'll let Kelsey answer this. With trimming, would you be worried about your model overfitting?
I think this can maybe kind of go both ways, because on the one hand, if you are removing outliers from your solution, you're not going to be fitting to noise, which sometimes overfitting happens because you get too fancy in fitting your training data and you start actually fitting noise at some point, which is why it doesn't generalize to new data. But at the same time, just like with any of these regularization parameters, I suppose you could go too far, maybe, or add too much. I think though, if you add too much trimming, you just end up with a really, really bad estimator because you've thrown out all of your data. Yeah, but so Sasha, who's also on our group putting together this tutorial, is the real expert. So if you have more questions, you can always post to the Slack channel and we can nudge him to answer if you have more specific questions, if that didn't answer your question.
I will just add that, yeah, I guess this level of trimming is itself like a hyperparameter. So similar to the way that you looked at the trade-off caused by the lambda variable in the lasso problem, where you had the fit and the level of sparsity, for example, with respect to each other trade-off. Here you can also have number of outliers and other concerns as well. So you can treat it as a hyperparameter too and try to tune for that. You try to use, for example, something like also cross-validation. It's a bit tricky also because depends what you define as outliers. Are you setting up statistical models to define outliers, or you will roughly mean something that doesn't fit our model? So the word outlier can mean different things. If you're interested in the statistics behind it, there are also references on that topic.
Mm-hmm. Yeah, and in this sense, the way that the trimming model is formulated, it's really looking at outliers as observations that have a really high error. Because in the optimization, the ones with high error, you want to have lower weights to get a better final function value.
Mm-hmm.
Yeah, and trimming's it's really well suited towards objective functions where it's a sum of losses for individual observations. So in terms of fitting like complex models, if it's set up as a sum of losses for different observations, all you have to do to incorporate trimming is just add these weights. So each term is weighted and you're solving for the weights while you are also fitting the model.
There are a couple more questions also about trimming. One of the questions is, could you talk about outlier detection and trimming in more complex models? Actually, I think you just mentioned that. Do you want to add anything else, Kelsey?
Well, I guess the formulation for trimming, like I said, is really nice for if you have like a sum of losses over all of your observations. But we also mentioned there's other ways to do outlier detection and removal besides trimming. So depending upon the type of model you're working on, maybe a different method for outlier detection might work better for a different model.
That's right. Another question asking, does trimming generalize easily to multivariate observations? Which is, again, along the same line. I think it means that the summation of, you don't have a separable loss function. I believe that's what they mean by multivariate. So it's not trivial how to generalize there, although there may be some extensions of this model. So yeah, this is one approach for outlier removal. this is not a full set of techniques. There are other techniques as well. So it's kind of an example. But I also repeat what Kelsey mentioned, that you can post more questions on this topic on the Slack channel, and we also get our specific expert on the topic answer them.
Yeah.
That's Sasha Arovkin, our colleague.
And we've also added a lot of references in the slides and in each of the notebooks. So if you're interested to learn more, you can dig into some of those references to get more information.
That's right. So I guess this concludes the material that we had prepared. Yeah, so as Kelsey mentioned, there are also references in the notebooks and in the slides. They're all available on GitHub. And please feel free to continue asking questions here in the Q&A window, or post questions or comments about the tutorial on the Slack channel afterwards. So let us wait to see if there are any other questions. Let's see, I think some more came in. So one question is asking, the solution vector reshaped into an image is fascinating. Could you talk a little bit more about that process? I'm thinking if there is a logistic regression to classify between 2 or more levels.
Yeah, this is.
So there are 2 questions. Yeah.
So that ends up sort of in brainland. Yeah, but it's right. Yeah, if your features are, in this case, they're asking about brain regions of interest. So it's a little bit of neuroimaging jargon there. Yeah, if you project that back to the brain, you would get the highest weights in, those pixels or voxels that are sort of the most informative. Is that right?
Right. So logistic regression, the example we showed was a super simple case because we wanted to give the intuition behind it. We only had 1 explanatory variable and 2 classes. This is the simplest case. You can certainly do more complicated. You can have more exploratory variables, and you can actually, you can generalize to more classes. The formulation gets more complicated. So our goal was to pick the simplest cases to try and give you a glimpse of what's going on behind the scenes. Why do these models work? And so that you can see the full expressions in front of you. But there are definitely extensions. And I guess the first part of the question, maybe Kelsey can answer that, about the process of how do you do it for images.
So for the MNIST example, the way our model was set up was that our solution vector that we were solving for went into the model as like a linear combination of the coefficients of the solution vector and the pixels in the image. And so since each, the solution vector is basically just like weights on the image values, it's really natural to then just plot those vectors in the position of the pixels that they're multiplied against. So it seems like you could definitely, if you're doing pretty much the same thing with like regions of the brain, you could just plot those coefficients in the regions of the brain that you're looking at. And really the only reason we take the like 2D solution and reshape it into a vector in the first place is really just convenience of plugging it then back into a model that we can solve.
And I'll just add this morning, or the talk that Gail gave earlier today about machine learning and neuroimaging, you saw a few of these maps, the maps that Gail showed of activation or sort of like weights of the SVMs. Those were maps of these kinds of features projected back, or feature weights projected back into the anatomy. Okay. Maybe
let's see.
at the bottom, there's a question from Jacob about scheduled learning rates.
I see. Yeah. So the question says, you discussed scheduled learning rates. That was in notebook 1. I've seen time-based decay, step-based decay, and exponential decay for learning rates. Do you have any thoughts on pros and cons and uses of different schedules and decays? Kelsey, would you like to?
I'm not a huge expert on this topic. Yeah, so there are different styles of learning rates, different formulations. I think you could dig into some of the links that we've posted, or ask questions on the Slack. That would be your best guess. Yeah, because I'm not a huge expert on pros and cons between different styles of learning rate schedules.
Mm-hmm. I would add that it very much depends on your problem. So if you have a convex problem, convex and smooth problem, we can say a lot about how to set your learning rates. If you have more complicated problems, sometimes there isn't much theory and it becomes more of a trial and error. So, but there are some guidelines. So hopefully our notebook 1 gives you at least a feeling about, for example, fixed step size in basic gradient descent seem to work, right? Especially when you pick it well based on Lipschitz constant of the gradient of the function. In stochastic gradient descent, it doesn't, and we use the decaying step size. So yeah, it all depends on what kind of problem setup you have.
Yeah, and then for gradient descent, also in the notebook, there's some links to information on choosing optimal step sizes. So this is different from learning rate schedules. For gradient descent, instead of a fixed step size, you can also have an adaptive step size, and there's different theories of how to choose that, like for a given direction, optimizing the step size, or for a given step size, even optimizing the direction. So there's a lot of really interesting topics that you can dig into on this.
Yeah, that's true. That's true. There's a lot that can be done. I mean, there is obviously also a whole set of other methods that would use, for example, second order derivative and curvature informations, which we didn't touch upon. These are the simplest, assuming only first order or gradient access to the function. Yeah, so it's a big topic.
There are 2 questions here about trimming, outlier detection, trimming in more complex models and multivariate observations. I think those are sort of related to each other. Maybe you could say something about that.
I
think we did discuss those.
Oh, you did answer those questions?
Yeah. Yeah, I think those were.
Okay, good. Sorry, I missed that.
Yeah, let me see. Is there another one? Was there a follow-up on one of the answered ones?
I think we can also take the follow-up discussion on Slack. I think if there are no other sort of new questions, then maybe we can break here. Thank you so much, Marianne and Kelsey and Prassana for preparing this and delivering it. That was great. And take care.
Thank you very much. Yes, it was really fun.